Alrighty, now let's take a look at question number 4. On question 4, we're going to be assessed on how to map shapes onto themselves with rigid transformations. We're just going to be focusing on reflections and rotations in this example. Alrighty, question number 4 reads, which transformation carries the parallelogram below onto itself? So we have parallelogram AMHT. Okay, so which transformation is going to carry this parallelogram onto itself? Alright, so in order for a parallelogram to be carried onto itself, basically when you carry out the transformation, the coordinates that we have here are going to match perfectly with the coordinates of the image of this shape after the transformation occurs. Alright, so that's how we can check numerically if a transformation maps a shape to itself. Alrighty, so let's write that down. In order for the parallelogram to be mapped to itself, all vertices, so these 4 vertices that we have here, must be mapped to themselves. Okay, either they end up where they came from, or every vertex is mapped exactly to another vertex. Okay, or onto another vertex of the original. So for example, if you have a rigid transformation that takes this point to this point and this point to that point, and those two stay the same, then it's perfectly fine. Okay, so that's just an example of a mapping that takes an object right to itself. So let's go ahead and carry out these 4 transformations on this parallelogram right here, and see which one generates a map that takes this parallelogram onto itself. Okay, so to get us started, we're going to make a table so we can keep our work organized. We're going to look at the mapping, and then we'll take a look at the we'll do the transformation first and then look at the mapping. So let's start with the transformation. We have 4 options to consider. We'll start with option number 1. For option number 1, we have a reflection over the y equals x line, over y equals x. Okay, so for a reflection over y equals x, reflection about y equals x, what happens is that the coordinate xy gets switched to yx. So you just interchange the coordinates. Alright? Okay, so what we're going to do is we're going to apply that formula to the mapping of the coordinates. Alright, so what we're going to do is we're going to pick the points one by one. We'll apply the transformation. If we get that point or any other point on the parallelogram, that's a pass. If we end up with a point that's not on this any of these vertices, then that point is a fail. Okay, so let's start with point A. Point A is 4, 3. We're going to apply this transformation on this point, which is a reflection about the line y equals x. When we apply the transformation, guess what? It's going to get interchanged to 3, 4. So the question is 3, 4 one of these vertices? The answer is no. Okay, so 3, 4 is a fail because this is not a vertex. What does that mean? Transformation number 1 fails. It's not the answer. So it cannot be this one because is mapping this vertex to some random point that's not a vertex, okay? So it doesn't map it onto itself. Moving on to the next one, option 2. Option 2 is a reflection, okay? A reflection over y equals negative x. Now, what's the formula for that? For the reflection over y equals negative x, for this one, what you do, if you have a point xy and you apply this transformation, it not only switches the axis, the coordinates, but it negates them also. So negative y, negative x is what you get when you reflect a point about the y equals negative x line. So let's test it out and see. Let's apply this transformation to point A again, 4, 3. If we apply the transformation, which is a reflection about the line y equals negative x, what's going to happen is that the coordinates will switch to, oopsie, not 4, 3. It's going to switch to 3, 4. It's not only going to interchange the coordinates, but it's going to negate them also. The opposite of the interchange. So this will be negative 3 and negative 4. Is this vertex, is it present on this parallelogram right here? The answer is no. We have another fail. Bam. This point is not a vertex. So this point 4, 3 is getting mapped somewhere else and is not mapped to this point or any other vertex. So what does that mean? This transformation does not carry this parallelogram onto itself. Moving along to the next one. The next one is, let's see, a rotation 90 degrees clockwise about the origin. Okay, that looks similar to what we did previously, I think on question 1 or something like that. So how do we do that transformation? For option 3 is a rotation 90 degrees clockwise. So for this one, rotation 90 degrees, not clockwise, sorry, counterclockwise. How does this affect a coordinate? So if you rotate 90 degrees clockwise about the origin, so if you rotate a point, let's say xy, 90 degrees clockwise about the origin, what's going to happen is that the coordinates gets interchanged, but only the y-axis is negated. Okay, so you negate the y-axis and interchange them. Alright, so let's apply this transformation onto point A and see what happens. So point A is 4, 3. If we apply this transformation, which is a 90-degree rotation about the origin, what's going to happen is that we're going to interchange the coordinates 3, 4 and negate the original y. So it's going to be negative 3, 4. Now, is negative 3, 4 any of those vertices right here? The answer is nope. Ladies and gentlemen, we have another fail. This is not a vertex. Not a vertex. Alright, so the last one that we're going to try out is the rotation 180 degrees counterclockwise. Ladies and gentlemen, this should be the answer by elimination, right? Hopefully. So what we're going to do is apply the transformation to the coordinates on this graph and see what happens. Option 4 is a rotation 180 degrees counterclockwise. Alright, so that one, rotation 180 degrees counterclockwise of a point xy. What that's going to do is simply going to negate the points negative x and negative y. Alrighty. Okay, so to do that, let's apply the procedure to the points. If you apply it to 4, 3, what's going to happen? If you apply a 180 degree rotation to 4, 3, that's going to give us negative 4, negative 3. Do we have that here? Yes. Point H. That's a check. Good. If you apply it to point M, which is negative 2, 3, you just negate the x, right? So this one is going to be, I'm sorry, you negate both of them. It's going to be 2, negative 3. Do we have 2, negative 3 here? Yes, we do. Point T. Check. All right, and then the next one we have A, M, H. H is negative 4, negative 3. When we apply the transformation, we're going to negate both of them. 4, 3. Do we have 4, 3 as a vertex? Yes. A. That's a check. And then the last one is T, 2, negative 3. When we apply the transformation, we negate both. Negative 2, comma 3. Do we have negative 2, comma 3? Yes. Point M. Check. So we can see that the transformation, which is a 180 degrees rotation counterclockwise, will map this shape onto itself. Okay? An easy way to do this is by, you can, for the rotation parts, you can just rotate your paper, and then ask yourself, how does the resulting image upon rotation compare with the original one? Or you can have a nice little paper, you just cut it out and then just rotate it and play around with it and see how um, the image upon rotation compares with the original. Alright, so in order to do this problem successfully numerically, you need to know what these formulas are. Okay, so this is basically how you map shapes onto themselves using rigid motion transformation. Thanks so much for taking the time to watch this presentation. Really appreciate it. We'd like to know what you think. If you found the contents of this presentation helpful to your preparation for the upcoming Regents exam, to give us a thumbs up. Your positive feedback is extremely important to us. If you have any questions or comments, just post it in the comment section below and we'll be more than glad to respond. Do not forget to subscribe to our channel so you can get updates to the remainder of this review series and other great math tutorials to help you do well in your math courses. And for more support resources, do visit our website at mathgotserved.com. Thanks again for watching and have a wonderful day. Goodbye.